Welcome to this video about doing computer vision for FIRST Robotics. My name is Dave LeMay, and I'm going to be talking today about the basics of computer vision and how we can use it for autonomous driving competitions. Autonomous driving is a huge area of interest for companies trying to develop self-driving cars. The tasks we are going to do are a lot simpler than that, but they involve the same techniques that automotive engineers use to develop the cars of the future. To encourage students to become familiar with those techniques, a FIRST Robotics competition usually involves a period of 10 or 15 seconds of autonomous driving, or driving with limited visibility where autonomous capabilities assist the drivers. There are many applications of vision possible, but we are going to talk about the most common case that we encounter in robotics competitions. FIRST Robotics usually has targets placed around the field marking important points, especially scoring locations. So our goal will be to locate those targets and then use the information about their location to drive our robot. How do we do that? To begin, we have to know a little bit about digital cameras and digital images. A digital camera includes a light sensor that determines how much light of a particular color is hitting the sensor. In fact, it usually has three such sensors for three different colors: red, blue, and green. When you take a picture using a digital camera, what you get is a file that has numbers corresponding to the light levels of each of the three colors. Computers work with numbers, so everything the computer does will be based on those sets of numbers. Now, back to our actual targets. Typically, they are rectangles of gray tape. However, it isn't any old tape. It's retroreflective tape. What does that mean? It means that if you shine a light on it, the light you shine on it will be reflected back in the direction it came from. How does it do that? Well, the answer is too long for this video. But remember that any line that passes through the center of a sphere passes through the surface of the sphere orthogonal to the surface. If you don't understand what that means, take a geometry class. That math stuff actually works. Anyway, suppose you have a light source shining on retroreflective tape, and the light from that source will be reflected back to the source. And that camera in the center of the circle will pick up the reflected light. And since it's reflected light, it will be the same color as the light source. So if you shine a green light onto retroreflective tape, the tape will appear green. And that is why most of our robots in FIRST that do vision have those green LED rings with a camera in the middle. How does that help? Let's get back to those numbers. Remember, we can represent any color by combinations of red, blue, and green. So maybe we ought to just look for things with a lot of green. Well, not so fast. Suppose I have a portion of an image with a lot of green and a lot of blue at the same points. It looks like this. That's right. You don't call that green. But there's a lot of green there. Looking for points with a lot of green is not the way to find green objects. Fortunately, scientists, artists, and computer programmers have studied this problem for a while, and they figured out ways to change those numbers for red, blue, and green into different numbers where all things that are green have similar numbers. That will allow our computer that works with numbers to pick out the green things. To make that work, scientists have defined a different set of numbers to represent colors, known as the hue, saturation, and value set of numbers, or more often called the HSV coordinate system. The value number represents the total brightness of the object. The saturation number represents the purity of the color. Colors with high saturation are more like primary colors, while pastel colors have very low saturation. Finally, there's a number for each different color called its hue. By convention, these colors are arranged in a circle, and the hue is represented by a number from 0 to 360. For reasons that aren't all that important now, you often see 0 to 180 or 0 to 255, but they all represent points on a circle. Now, we are ready to find green things. Some people have made an excellent program for use in FIRST Robotics to make selecting the value that represent the colors that we want easier. The program is called GRIP, and it's a free download for Windows. If you do computer vision, whether or not it's part of FIRST Robotics, you need this program. It's the best of its kind except for the very expensive professional packages. To illustrate how to use GRIP, I'm going to actually do a different problem. I'm going to see how to find the orange balls used as cargo in the 2019 game. This picture shows the image that we gathered by our camera. We can import that picture into GRIP as an image source and manipulate it. We're going to take away everything that doesn't look like a cargo ball. GRIP has lots of operations it can do. One of those things is to throw out things that don't have specific color parameters in the HSV space. So we'll set up a color filter. We want orange things. The panel to the right of the original images shows all the pixels that pass the color filter. At the beginning, all pixels pass the color filter, so it's all white. We have to throw out things that don't look like cargo, so let's begin by noting that orange is not a pastel color. It is a very distinct and not much like white at all. In other words, it has high saturation. Let's set the saturation value to high. Okay, that got rid of a lot of things. But there are plenty of pure colors in the image. We need to do more. Well, we also note that the ball is pretty bright. A lot of other spaces are in shadow or not well lit. Let's say that we don't want pixels that have a low value. That got rid of more, although it did lose some pixels in the bottom of the ball where the shadows fell. Finally, we only want orange pixels. Orange is a lot like red, and it has a value somewhere around 10 for its hue. We'll use that. Okay, so now we have most of the ball and not much else. Unfortunately, we did lose parts of the ball, and there are a few things out there that aren't part of the ball but passed our filter. That guy wearing the orange shirt definitely got included, but so did some flesh colors. They really don't look orange, but they have very similar hue numbers or very close to orange. Selecting the exact filter can be difficult, and it never works perfectly. There are several other operations we have to do to get exactly what we want. To illustrate, let's go back to finding the targets. We use a few more tricks to find those targets, and I don't have time to describe them. Basically, we change a few things about the camera so that we never even see a lot of the image. After we do that, our vision targets look like this to our camera. Now, we set up our colors for bright, saturated green pixels. The result looks like this. What next? Well, let's have another diversion. How are we going to make all of this work? How do we write code for the computer that will get the results that we want? The answer is that there is an open source library of computer vision functions called OpenCV. GRIP is just a shell program that calls OpenCV functions, but it doesn't have every single function. We'll write code to do what we need that calls OpenCV functions and also uses regular logic functions to sort through the results. The code I'll show in this video is in Python, but OpenCV also supports C++ and Java. Don't worry about the exact calls I'm going to show in the video. The important thing to know is that if you can describe the shape of something using lines or rectangles or circles or some other geometric shape, OpenCV probably has a function to find that shape for you. The first thing we'll do is note that the targets we're looking for are big connected regions. OpenCV has functions for finding the boundaries of that sort of region. Those boundaries are called contours. Once we have the contours, OpenCV also has functions that can retrieve the size and shape of the contours. We're going to first get the contours. Then, we'll find the biggest contours. We are most interested in objects close to us, which should be the biggest. Once we've found the biggest targets, we want to find their corners. However, if you look at the contours, you can see that they aren't perfectly rectangular. Some of the pixels on the outside of the tape have been omitted. We have to find some trick, and the one that we will use will be that we know the missing pixels are on the edges, and we know that the real shape of the contour is a rectangle. If we have the smallest rectangle that contains all the points, that rectangle will match up very closely with the real edges on the tape. You guessed it, OpenCV has a function for that. Min area bounding rect will give us the answers. Now, we know the 2D position of the targets. From the game description, we also know the 3D position of the targets in the real world. Can we use that information? Yes, of course we can. What we have to do is figure out the distance from the camera to the target that would cause the 3D object to be projected onto the observed points in the camera image. Using the equations for 3D projection, we can find the distance with the nearest projection to the observed image. For all positions, we can write down an expression for the error position, which is determined from the sum of the squares of the error estimates for each point. After we differentiate the expression and set the value to 0, we can solve that set of equations. This process is called linear regression, and at the end, we get the value that minimizes the error over the range of all points, and that is our estimated position. Did you get all that? Yeah, me neither. Fortunately, we're using an open source library. Somebody already did all that work for us. We call the OpenCV function solvePNP. For arguments, it takes the 2D position of the points in an image, the 3D position of points in the real world, and some parameters that describe the camera and lens. And it tells you the 3D position of the camera with respect to the target. If you know the 3D position of the camera, which you know is on the robot, you know the distance and angle from the robot to the target, and you can drive toward the target. There's a lot more to talk about, and some details we left out, but that's all the time we have for this overview video. Try this out yourselves. We have a camera, and an OpenCV program is written to do all of these calculations. Use the camera and that program to determine the distance and the orientation of a camera to a target. You'll find it easier to do if you mount the camera to a tripod instead of a robot, but any fixed known position of the camera will do. Good luck! Let's see your results.